Our first topic, our first lecture, concerns least squares and curve fitting. Now, I have a monograph to go with this entire, wait for it, least squares and curve fitting, which you need to read and follow along. And this is sort of a lecture to kind of elucidate and to bring out some of the points that I make in least squares and curve fitting. The ability, this is one of those things where everybody knows what they're doing, but they really don't know what they're doing. Because they've many times the way they've been taught or the way they understand doesn't line up with the math, and in turn they also at the same time take their spreadsheets, they simply blindly pick an answer and they then apply it, and it doesn't really help them and they don't know why. And I'm going to talk about why. Let's start with the obvious. Let's start with lines. Let's start with straight lines. I have 2 points, x1, y1, and x2, y2. And we might as well put some axes while we're at it, x-axis and the y-axis. I have 2 points on this. Now, what can I do to make some sense out of these points? Well, what I can do is to draw a line between them. It should be, and the equation of a line is y is equal to x plus b. I can, if I know these 2 points, I can actually, a line can be defined by simply 2 points. That's basic geometry. Mathematically, I would say that y1 is equal to mx1 plus b, and y2 is equal to mx2 plus b. I have 2 equations, 2 unknowns. In this case, the m and the b are the unknowns. The m being the slope, and the b, if I extrapolate this point back to the y-axis, the y-intercept. That's pretty basic. And if I can know if I can solve 2 equations and 2 unknowns. If I use a little linear algebra and set this thing up, it looks something like this. And I've got notes over here, so that's why you see these me looking at them. x1, x2, 1, 1, and then m and b is equal to y1 and y2. That may not be obvious up front if you're familiar with it, but that's taking this, you get this. Now, everything is good. I have a situation where I have a square invertible matrix, and I'm not here to do a lot of linear algebra theory. I have some very strong opinions on how linear algebra is taught that probably won't sit well with some of your math professors, but in any event, you've got a square, m and b, y1. What the point of this is that with this setup, if I can invert this matrix over here and multiply it out, I can actually determine m and b. So what do? I take and I invert this thing. And I will end up with, oops, too happy with this thing, will equal to the inverse And the last number in the matrix entry is I'll multiply this by, and if I did all this, I would end up with something that looked like this. And like I said, I'm going to make sure I have notes so I over all right, and I now have this. This is m, the slope, which is simply the rise this way over the run this way. Pretty basic. And this is my y-intercept. I can do this for any any number of pairs of points. I can get linear interpolation, and this is basically, I can now that I have m and b, for any point along this line, it goes both this way and this way, I can find a point on that line. For any value of x, I can find a y value for it, or revert, if I reverse it. Doesn't matter. So that is basically linear interpolation. I can do, now I know, for those of you who are into Lagrange interpolation, there's a little different approach, but basically the results are the same with 2 points. Now, that's terrific until we consider the following. Now let's consider the problem of 3 points. 3 points, as you can see, and I'm going to refer you to my printed notes or article on the subject. This cannot be defined with a line, at least reliable. I mean, it's possible that if this point is determined after you find this line, and it's on this line, yes, it is. But if you've got just 3 points, you cannot guarantee that they're going to be collinear. You just can't. What you can, however, do, if you really want to, is draw this. And basically, the equation for this is I add a squared term. And I show you that we can, for any 3 lines, we can use a second order equation, better known as a parabola to some of you, to determine a line that will go through all 3 points. You can pick any 3 points and get this result. So if you keep going with this and actually use sort of an inductive type of approach, if I have 4 points, I can use a cubic equation. If I have 5 points, I can use a quadratic. In other words, for any number of points, you can have you can have some kind of equation of 1 power less than the number of points. Or maybe, to put it another way, the number of segments between the points. You can have that. Now, that's great, except for 2 problems. One of them is this, and this is a favorite one of the students, and I've seen this over the years. Let's just forget about having 3 points. Let's say we have this number, that's 5 points. A valid interpolant would be, a sensible interpolant would be one that looks like this. And your spreadsheet might come up with that, and it might not. On the other hand, another valid interpolant would be that. It passes through all 5 lines, 5 points. Why not? That's my point. Whether it's a valid interpolant it may not be a meaningful one. That's one reason why you should not blindly take what you get out of your spreadsheet and run with it. And the other thing is, when you're trying to correlate data, is this a particularly good way of doing that? It's valid and it's precise, but is it accurate? If, for example, I have something a little bit closer to reality where I have points like this, I have 5 points, fourth order equation. If I get this, first of all, it's not very meaningful, and second of all, it has to go through the point. Second of all, it doesn't really, if I'm trying to correlate data in reality, it's not really too mean. And the use of fourth order and up equations really is not, it can be used for most applications. It doesn't really tell us much. So, what do we do? I mean, you can produce, say you've got 20 data points. Is a 19th order polynomial really what you want to present? Knowing that data, and if you don't know that data can vary can vary and have ups and downs and inaccuracies, if you don't know that before this course, you'll find it out real quick. I can guarantee it. Maybe what this really represents is something like that, where instead of having a fourth order polynomial, I have a line, and it's not an exact fit. But given the inaccuracies of the data and the variations in the conditions, it gives me a better idea in many ways of what's going on than the fourth order polynomial, which is probably better at documenting the inaccuracies of my test procedure than it is in actually giving me an understanding of what's happening. How do I get to this? Well, in a linear algebra sense, I'll show you. And I'm going to use the 3 points to illustrate what I'm talking about. Let's say we have 3 points. Now, I already know that, I already know that I could do a parabola and live happily ever after. But I also look at these as, they probably are linear. So how do I find the best fit? Well, this is what if I put it in matrix form, it's going to look like this. I have x1, x2, x3 times, which m over b is that line, is equal to y1, y2. Now, there is no unique solution for this. This is not a square matrix. It's not invertible, at least not in the proper sense of the word. And there's no unique solution for this. But let's suppose that I sneak in a term that looks something like this. If I did that, then I could have a solution. And if I could somehow, and that would be basically what that looks like is this. If I put a line through here, and this is very conceptual. I'll just warn everybody of that going in. This is very conceptual. Each one of these points varies some from the line, and that variation is represented in this. Now the question arises, how can I, what I want to do is I want to minimize this residual so that this line will be the best fit. It's not necessarily the perfect fit for this data, but it is the best fit, given the restrictions I've put on in terms of the form of the solution. And this can be done for lines, and any of the parabolas can be done this way, and any of these can be, any order polynomial solution can be done this way. If I have, for example, 50 data points, I could use this with a 10th order polynomial. Although 10th order polynomials are not very practical, and they're not necessarily very educational in terms of what we're trying to accomplish. Usually, we'll talk about the other alternatives later. But probably for most of you, and the technology has changed to the point where this is largely invisible to most users. Probably the best, the one we see all the time, literally, is digital photography. If you're familiar at all with file formats, you know that there are two types breaking down into lossy and lossless. A lossless is basically they take basically all digital photographs are an array of pixels. And these pixels are different colors, have different color selections. And that selection can be those can be very large. If I take a lossless, basically what I'm doing is I have a square matrix of some kind here, I multiply it by a matrix of the same, or by a vector of the same order here, and I guess, in other words, I invert it. I've not lost anything in the compression process, because uncompressed images are huge, and very huge, in fact. If I compress them, a lossless compression preserves all the data in the loss. And you can do that by repeating pixels and whatnot. However, if you use a lossy compression, JPEG is the best known of those, and there are others, you see those particularly in video, then if I have a lossy compression, my job is going to be, I'm going to lose some stuff. And that loss is in the residual, and I want to minimize that loss. Or, and how much loss I can stand depends on the quality of the image I want. A low quality image will have a high residual. High quality will have a low residual. And a lossless compression will have no residual. So that's an illustration that you see all the time. But getting back to this, the question is, how do I minimize this? I have, in this case, 3 numbers. I could have more. I could have 20, 30, 40 numbers, whatever. Obviously, the more data points you have, the more chance you have for statistical significance. And that's always nice to have. So therefore, I say, well, how do I know it? Well, this is where we invoke something called a vector norm. These are matrices and these are vectors. Just to be cut to the chase real fast. And basically a vector norm is I take a series of numbers and I reduce them to a quantity that I can use to compare one vector with another. Okay, question is, what then is the vector norm that I can use? How do I reduce these to a single number? There are 3 norms which are traditionally used, or at least most commonly used, let's put it that way. The first one is called an infinity norm. Infinity norm says, I'm going to adjust these values to the point where the largest value is minimized. In other words, large, small. And by the way, usually, in some ways, I take an absolute value of those. I don't care if it's below or above, it's off for statistical purposes. So I'm not worried. Infinity norm you don't see it very often. You don't see it, it's not very useful to us. The second thing is a one norm. A one norm is where I take the absolute value of these and I add them up. And I try to find a combination, in this case they have m and b, or whatever parameters I have here, such that that will be a minimum. One norm minimum optimization is very useful in some applications, but it has issues, not the least of which is that the point of optimum point is not differentiable. The reason why it's not differentiable is because one norms come, basically v like this. That's not differentiable. Which means that many optimization techniques you use to find this thing don't work very nicely down there. There are actually certain applications where one norm is used. There are, and it's kind of the obvious one, but we don't see it very often. There are some, the one big plus, and I'll explain in a minute, is the fact that one norm is better at dealing with outliers in the data than, say, two norm optimization, which I'm about to discuss. That leads me to two norm, and I'm going to come back to that in a second. Two norm optimization is basically where I take the sum of Rn squared, R1 squared plus R2 squared plus R3 squared. Sometimes I'll take the square root, that which kind of it makes you think of a triangle, which is why it's called the Euclidean norm in many cases. And sometimes I'll divide it by the summation of the absolute value of R or whatever. But any way you slice it, it's the sum of the squares of the residuals. And I'm going to try to minimize the sum of the squares. Two norm optimization is what is that point. Instead of being that, it looks like this. It's differentiable at that point. Two norm optimization is what, if you ask your spreadsheet to give you a trend line, that's what it's going to use to do it. And that can be done by hand, and usually I now assign the requirement to do it by hand, and I have features and videos on how you do two norm optimization by hand. Because one of the nice things, particularly with lines and whatnot, is that the optimization of that has a closed form solution. Okay, with that out of the way, there's one other thing I want to talk about. Most of you who have done least squares analysis on your spreadsheets or trend lines have noticed that they ask you whether you want log, power, or whatever, different types of correlations. You ask, what's that all about? All right, for linear interpolation in any higher order interpolation, parabolic, cubic, whatever, and then normally I restrict my students to cubic for the purposes of this lab. They don't always stick with that restriction, but that's what I do. Now the question obviously arises, what's this logarithmic all about? Okay, if I have back in the dark ages, when dinosaurs ruled the earth, I would have log, and your spreadsheet will actually let you do this, although now I'm not, it's helpful in some cases, logarithmic scale. It'll actually give you a logarithmic scale for the x or the y-axis or both. And actually, there are some applications where that's nice. For this lab, not so much. What that basically amounts to, instead of plotting x versus y, they would either common or natural. And basically what I had there for is that instead of doing this with y is equal to mx plus b, I have ln and y, and I'll use the common. In other words, a straight line. But if I were to take the e power of both sides, I will end up with an equation that looks like this. Basically, that's an exponential equation. It's for only one of the graph axes is logarithmic, and therefore y is equal to b, y has equal to b m to mx. It's a change of variables to get to a logarithmic, to an exponential, to an exponential equation. If I put these in and apply the change of variables, I can map it with exponentially. I can also do the same thing if I start with common logs. And by the way, engineers in the past, and a lot of and this is kind of hangs over a lot of our methodology, have always had an allergy for natural logs until in many engineering disciplines. I know my specialty is part of geotechnical engineering, and geotech has always had an allergy for common law. At least in the United States it has. That does to this equation, y hat, and actually these all should be hatted as well, is equal to b hat times 10 to the mx, to the 10th power. As opposed to the e power, it goes to 10th power. So you can do either one, whichever one. Usually what happens to you is if you do this, then it's pretty much the same both ways. It's just that people were more used to common logs in the past, and that's how they did it. Well, is that all you can do? Well, not really, because if now I have all of this. If, for example, I decide to really go over the top and log or ln x, then I would have this. Let's see, make sure. Yep. Which goes back to that power relationship. Both of these are log, therefore you get a power relationship. In the past we used log paper. And that can be very useful for certain applications depending upon how the data goes. But when your spreadsheet asks you if you want, and there's also correlations for saturation growth equations and that kind of thing. But in any event, when your spreadsheet asks you whether you want a log or a power or an exponential, this is what it's doing. It's basically exercising a change of variables. And it's allowing you a little more flexibility in how you want. And these are very useful because they're fairly easy to use and set up. The only tricky part is that on either log or semi-log, any 0 point is pretty much out the window. Other than that, they can be very, very useful. So in conclusion, we have this. First, you now see how least squares curve fitting, or curve fitting in general, is different from interpolation. When your spreadsheets like interpolation, they use it for smoothing and these fancy curves that they produce. But it has limitations, and it can be misleading. For practical purposes and for data reduction purposes, curve fitting is, using the best solution rather than the exact solution is in general the best way to go about data reduction. But second, whether it's interpolation, curve fitting, whatever, don't take whatever your spreadsheet throws at you and accept it as fact. Spreadsheets do not understand your physical application. And if you're using Google Sheets, Google will not tell you that's the stupidest data reduction that I've ever seen. They just won't. Look at your data when you get it and see if it makes sense to you. is, for example, as an extreme, say it'll give you 8th or 10th order polynomial. It will align to it, or whether it's something else. The beauty of a spreadsheet is that you can try different things and see how they work, rather than just having to go back and crunch a bunch of numbers all over again, like we've done in the past, or replot it on paper. And one of the things I've noticed in teaching is that plotting on paper is a lost art with with many of our students, and that through no fault of your own. Computer graphics have made stuff simple. But look at your results. Don't just take blindly what is accepted. So, next time we'll start applying some of this, but in the meanwhile, thanks for watching and God bless.